Okay, well, hello everyone. I'm going to talk about our paper determining the acceptability of abstract arguments with graph convolutional networks. What this paper explores is an approximate approach to solving classic Dung argumentation frameworks using graph convolutional networks, which is a variant of graph neural networks that has been quite successful in a number of other domains. It uses this approach on effectively sort of two classic problems, which is skeptical and credulous acceptability under the preferred semantic on a data set that has been taken from the second international competition on computational models of argumentation. We managed to get relatively good accuracy, up to 92.68% on credulous acceptability, 97.15% on skeptical acceptability, which is somewhat better than a previous feasibility study done by other authors in this field. We do that principally by introducing a new way of randomizing our training regime to learn better from graph structure. A lot of approaches in graph convolutional networks relies on features on the vertices or the nodes of the graph, and obviously you don't have that in abstract argumentation graphs. So we've had to maximize for learning from graph structure on its own. So I've got some definitions. I don't think I have to go through those in this forum, but it's just to say that what we're dealing with are classic Dung abstract argumentation frameworks, and we're dealing with acceptability under the preferred semantic, and for both skeptical and credulous cases. So convolutional graph neural networks have been inspired by the success of convolutional neural networks in computer vision. So obviously many of the advances in recent years in computer vision on ImageNet or similar competitions have been due to very deep convolutional neural networks. Now, obviously you can decide to interpret a graph, an image, as effectively just a particular kind of graph, but most graphs do not have the properties that sort of traditional Euclidean images have. So modeling convolution in this context is not trivial. There are sort of two main approaches that have appeared. One is the spectral approach, which is based on graph signal processing, so that effectively applies a filter to a matrix-based representation of the graph. And the other approach is a spatial, it's based on a spatial metaphor where you're effectively aggregating neighborhood information from some neighborhood around each node in the network. The method that we're using, the sort of traditional graph convolutional neural network, can actually be interpreted as either. If you see the definition down here, you're effectively calculating the graph convolution by taking the sort of weighted average of the neighborhood information, and then applying an activation function to it, and then aggregating that across all nodes. So our overall architecture is quite close to traditional approaches for graph convolutional networks. We create a set of effectively random node embeddings, and we feed the adjacency matrix in a normalized format into the input. And then we feed that through a set of convolutional layers. And after that, we feed it to an output layer which generates a prediction. In this case, it's just a prediction, a number between 0 and 1 that tells you how likely the network thinks it is that a given argument in the input is acceptable. We do add at each layer additional information relative to what you would normally do. So we add the original input features, and we add the normalized adjacency matrix at each step and at each layer, because when you're dealing with depth in this type of network, it's very easy to get either vanishing gradients where your the signal just becomes lost, it becomes too attenuated over time, or you get over smoothing where effectively everything tends to converge to the same point. So to correct for that, we add what are called residual features at each layer in order to preserve all of the structural information. So in addition to that, we have made a number of changes to the way that we train this type of network. So we've introduced a randomized training scheme where effectively we feed a set of argumentation graphs at the same time to the neural network. And then we generate a randomized training mask asking it to predict the acceptability status of a certain subset of the arguments across all of these graphs chosen at random. And what that means, what that does is it effectively prevents the neural network from memorizing or from overfitting to a particular thing. And with abstract argumentation frameworks, it's a binary decision problem whether something is acceptable or not, but it tends to be quite heavily skewed. So it tends to be many more non-acceptable arguments than acceptable arguments in most argumentation frameworks. And that's worse for skeptical versus credulous acceptability, of course. So that can make it very hard to train a neural network, because actually just saying no can be a very good strategy, and it's quite an easy strategy to end up learning. So we've introduced this function to encourage the network to generalize from the structure of the graphs as opposed to just learning a single answer. In a similar line, we've also introduced a function to dynamically balance this training mask so that we can say that it has equal amounts of non-acceptable and acceptable arguments in each training mask that it generates. We've also there are some argumentation frameworks that effectively have none or only a single acceptable argument in the training set that we've used. So we've basically excluded the very extreme outliers from the training, but not from the test. They still form part of the evaluation. These measures were not used throughout, so I'll go into that a little bit later. So as I said, the graph convolutional networks, they have this suspended animation problem where they converge to a fixed point and stop responding to training data after a certain amount of a certain number of layers. As I already discussed, we added these residual connections in the neural network architecture to overcome that problem. So the data set that we used consisted of 900 argumentation frameworks from the ICCMA's 2017 competition, including all 5 difficulty categories. We had input frameworks up to 15,605 arguments and 6.25 million attacks. The average, as you can see, was somewhat lower, but still quite sizable. Now that also meant that we had to split training into separate folds. So we're effectively training on 100 graphs at a time, and that's simply a memory limitation. We dynamically split between training and validation sets, and then we withheld 10% of the training data as a test set. So we trained 5 models. We trained 3 layers that are effectively identical except for the number of layers. So we trained one with 4, 5, and 6 layers that did not use the balancing mechanism I described, but did use the randomization and the residual connections. Then we had an example where we used both the balancing and the randomization, and we also had one where we did not use the randomization or the balancing to enable us to compare the different setups for the model. So overall, on the problem of credulous acceptability, you'll see that the best overall accuracy is actually for the model that does not use any of the additional features that we've introduced, but that is because that network has, for all intents and purposes, just learned to say no, right? It gets no right in 99.7% of the time. It gets yes right in 7% of the time. So in practice, that's not a usable model, because like all it's learned is that we're dealing with an unbalanced data set. Among the rest of them, you can sort of choose between the 4-layer and the 5-layer GCN based on your preference for slightly higher overall accuracy or slightly better balance between yes and no. But in general, like the accuracy is relatively good. It's probably not where it needs to be for deployment in a real world production scenario, but it is relatively good. If we look at skeptical acceptability, it suffers from the issue that skeptical acceptability is even more skewed than credulous acceptability. So it's much the same phenomenon, just more extreme. So what we see here is that the data balancing has a much greater effect in the skeptical case, and that is almost certainly because of the greater degree of skew. Now, depth, interestingly, did not seem to matter much in our scenario. Effectively, what depth does in this type of architecture is it increases your receptive field. So probably when you've got 4 layers, the receptive field is wide enough that there will be relatively few arguments whose acceptability status is determined by an argument more than 4 hops away. And that's why we don't see greater improvement to depth would be my guess. I don't have strong evidence for that, but that would be my guess at this point. Something we need to investigate further. The randomization and balancing. Overall, you actually do get better overall accuracy by just saying no, but again, not useful in practice. So the randomization and balancing features are very important in achieving a better distribution of accuracy between yes and no. And finally, runtime performance. This is very attractive runtime performance. It's probably one of the main reasons to even explore this type of approach. You can effectively classify millions of arguments across multiple graphs within seconds. So for very large scale scenarios where classic solution approaches simply would not be able to compute results in an adequate amount of time, this type of approach might be able to be useful in practice. So we are sort of improving the results for this type of approximate approach. we still need to have better balancing of the classes and probably also a little bit higher overall approaches, but that is effectively sort of what we need to work on future. And again, the randomized training regime seems to be the main contributing factor. And that type of training regime may have applicability beyond this particular domain. I think that was it for me.